Okay, this is work with Shiyuan Zhao at UC Irvine, and the data is from Baseball Savant and Brooks Baseball. And the goal here is to put a number on the similarity of players based on distributions defined over parameters measured by ball tracking systems, with the motivation being that these parameters are intrinsic to player skill. And there's a number of applications that we can address with this. We can optimize performance and health projections. We can generate larger samples for modeling matchups. We can compare players across time and competition level. And a special case of this, we can monitor individual players over time, and we can relate distributions and performance. So if we have a guy's collection of pitches, we can say, for example, that this pitcher should be throwing, say, 3% more changeups to left-handed batters, that kind of thing. Previous work, we start with Bill James and his similarity scores, and Nate Silver had player comparables that were used in PECOTA. Those came before we had ball tracking data, and then after PitchFX came along, we've had a number of efforts on measuring pitcher similarity. Josh Kalk, Stephen Loftus, Vince Gennaro, and we've built upon that work for measuring pitcher similarity. So I'm going to talk about that, and then I'm going to talk about how we can use a related method for comparing batters. For PitchFX and TrackMan, we get for every pitch the speed, the horizontal movement, and the vertical movement. And I get asked sometimes, are these parameters actually important? And the data tells us that yes, these parameters are important. Here is an example of the importance of adding a mile per hour on a fastball, fixing all the other parameters. So we're fixing here the count, the platoon configuration, the vertical location, the X and Z movement, just increasing the velocity as a function of the horizontal location. And this is run value here, so you can see as we add a mile per hour on a fastball, we can quantify exactly how much the pitcher gains from that. We can do the same thing with movement. This is fixing all of the parameters and just increasing the amount of vertical movement from, say, 6 to 9 inches, and we see the benefit that the pitcher gets. So given that these parameters are important, the speed and the movement, we can now take a pitch represented by these three parameters and plot it as a point in a cube. Dimensions, of course, speed, vertical, horizontal movement. And what we've got on the left is 1,000 John Lester pitches from 2016. The different colors are the different pitch types. And then on the right, we've got 1,000 Chris Sale pitches from 2016. And we compare these distributions using what's known as the earth mover's distance. So what that does with the pitch cubes is it figures out how much work is required to move, in this case, all of Lester's pitches, so that as a group, they end up at the same location as Sale's pitches. So if the distributions are exactly the same, then no work is required to move the pitches. We get a distance of 0. As you start to move the distributions further apart, then it takes more work to make them the same, and we're going to get a bigger distance. So that's what we're going to be using for similarity. Now, things are a little bit more complicated because the amount of work that you have to do to move a pitch depends on the direction that you're trying to move it inside of that cube. So for example, if we take a pitch, here we've got a scatter plot of speed, pitch speed, and vertical movement, and we've plotted some specific pitches. And if we try to take the pitch here at this orange spot and move it with the flow towards the red spot, that's going to be easier than trying to move the orange pitch in the direction of the green spot, going against the flow because of the way these variables are correlated. So what we can do is we use a Whitening Transform, and the Whitening Transform corrects for the fact that these variables are in different units and they have different variances, and it also corrects for the correlation of the variables. And it can be implemented, if you're familiar with the Mahalanobis distance that's given here. The sigma is the covariance matrix of the three variables. And what we do is we compute this whitened earth mover's distance separately for pitchers against right-handed batters, that's the distance here, and against left-handed batters, and then we weight them by the league average fraction of pitches thrown by this constant's right-handed pitchers to right-handed batters, and this is right-handers to left-handed batters. and then we add that together and we get the overall distance metric. And it turns out the most similar right-handers in 2016 were Matt Harvey and Shelby Miller, two guys that came up together in 2012. By 2013 were regarded as two of the top young pitchers in the game. They've had health issues since then. The most similar left-handers we got for 2016 were John Neese and Chris Russin. Turns out those two guys were born 5 days apart back in 1986 during the World Series. And if you want to get the most similar pitchers for any pitchers, you can go to Baseball Prospectus, and there's tables there that you can get all this information. What I've got here is a plot of the most unique right-handers for 2016. What unique means that we can get from this metric is it means that there's a large distance between the pitcher and the nearest other pitcher, kind of what you'd think of for the definition of unique. So here we've got the 10 most unique right-handers. We also put in the two knuckleballers, Wright and Dickey, who would be unique if it wasn't for each other. And we can take our array of distances, and to get an idea of what things look like, we can map them to a lower dimensional space using non-metric multidimensional scaling. That's this NMDS. And to make it easy to visualize, we're just mapping to the plane in 2 dimensions. So it's an approximation, but it gives an idea. And in this plot, pitch speed increase is going down, and vertical movement increase is going to the left. So for example, the most unique pitcher in this set is Brad Ziegler. He shows up here at low speed and very heavy sink. The hardest thrower in this set is Brian Shaw down here near the bottom. You got Wright and Dickey with the knuckleballs here, Jared Weaver not too far from them. And then here we've got 3 guys who threw a lot of four-seam fastballs that has the large vertical movement Z at that side of the space. And we can put everybody on this picture, and in fact at one point we did, but then it gets too busy to be able to see anything. But if you're interested in particular people, you can put them on the picture. The left-handers look like this for 2016. Zach Britton was the most unique with its very hard sinkers, so he shows up on the right edge. A couple guys in the top right that throw a lot of sinkers, but not as hard. Chapman shows up at the bottom with his very high velocity, and we've got 4 guys on the left edge that throw a significant fraction of four seams with the larger Z, and the four-seam velocity increases as we go from top to bottom among these 4. Now, it's nice to be able to make pictures and leaderboards and things, but what can we actually use this for? So I'm going to talk about one of the applications, and this is using this for forecasting. And the idea is that if we want to try and estimate the talent level for a player for a given statistic, say for pitcher's strikeout rate, the best estimate of the player's talent for strikeout rate is not his observed strikeout rate, but rather it's that observed rate that's regressed in the direction of the population mean. So what we can do with a similarity measure is we can define more appropriate populations for doing this regression. And I'll explain how that works with some examples as we go. Some of the previous work in this area, there's a nice paper in Scientific American that explains the statistics. In the book, they work out a lot of the math related to regression. And then more recently, I've written a paper that talks about how to use this for batted ball statistics. So here is the idea. This is strikeout rate for right-handed pitchers against right-handed batters in 2015 and 2016. Our K rate is strikeouts per batters faced, with pitchers as batters taken out and with intentional walks taken out. So each point in this plot is a particular right-handed pitcher, and where the point is tells us what his strikeout rate is for the 2 seasons. So the outliers, this is Scherzer up here, this is Mike Pelfrey down here. The way that regression typically works is if we have a guy's strikeout rate for, say, 2015, maybe it's here, our best guess for 2016 is to just go up to the regression line and say that is our best forecast for 2016. And the issue, of course, when you look at this, there's a lot of scatter about the regression line, which means that you have the potential to make significant errors in your forecasts if you're doing it like this. So what can we do with a similarity measure? So what we've got here is Chris Archer and the 7 most similar right-handed pitchers against right-handed batters in 2015, and then we've plotted these 8 guys, their strikeout rates in 2015 and 2016 against right-handed batters. And Archer is known as a guy that has pretty good stuff. His most similar pitchers here are guys like DeGrom and Pineda and Strasburg, so also guys, as you would expect, that have pretty good stuff. And if you look at the regression line we get for just this set, it has a stronger slope. This has a slope of about 1. The original one had a slope of about 0.7 with all of the pitchers, which means that if somebody has Archer-type stuff, and they have a good strikeout rate, we expect that strikeout rate to hold up pretty well from year to year without as much need for regression. So we're combining the idea of regression with what we measure from StatCast and using that to look at similar players. If we go to another one, this is Giovanni Guyardo as of 2015. He was not known at that point as a guy with great stuff, and you see here that we get a line that's got a much weaker slope. It's almost horizontal, meaning that if you have a good strikeout rate but you have this kind of stuff, we're not really buying it going forward. And then this is another one. This is Felix in 2015, so he started to decline a little bit, but he's still Felix, so this is somewhat in between Archer and Guyardo. So let us look at how we can use this for regression, just one example. What we've got here is a couple pitchers, Michael Pineda and Trevor Bauer, who had nearly identical strikeout rates. Again, this is right against right in 2015, and then in 2016, Pineda got a little bit better, Bauer got quite a bit worse. And the question is, how can we try and figure that out, that that's what's going to happen? So in the plot, this is the same scatter plot as before. That is Pineda, and then Bauer is here. And if we do the full regression, we've got the full regression line here, Pineda would end up at the regression line, and so would Bauer. And since they started off about the same in 2015, they're going to end up with about the same regressed prediction for 2016, shown here, right around that point there on the regression line. Bauer comes out with a slightly higher forecast because he was a little bit higher in 2015, so he's a little bit further up the line, but we see we get fairly significant errors here. If we do the group regression, Pineda, as we said, was part of the Archer group, so he's not going to get regressed all the way down to the line. He's just going to get brought to the red point, so the idea is the red point is closer to that black point than the regression line is to that black point. And then we do the same thing for Bauer. Bauer was in the Guyardo group, so his group regression is at green point. And the idea is that the green point is closer to the black point than the regression line is to the black point. And if you like numbers, the numbers are over here. Using the group regression, where the groups are generated by the similarity measure, we can get a much more accurate estimate of the talent level and a much more accurate estimate for the forecast moving forward. Okay, so we can do the same thing for batters using batted ball data. And from StatCast, we get the exit speed, we get the vertical launch angle, we get the horizontal spray angle, and the batted ball spin rate. And we know, of course, from the Woba cube that the value of a batted ball depends on certainly the exit speed and the 2 angles. It's a fairly complicated function of those 3, but these variables are all important. So here, it turns out what we can get from Baseball Savant is only the exit speed and the vertical launch angle, which are the 2 most important of the 4, but that's what we're going to be looking at. And here's a scatter plot for 2017 against right-handed pitching for a couple of Yankees. Aaron Judge is the black spots. Ronald Torreyes is the red spots. So just exit speed and launch angle. And you can see that Judge has a significantly higher average exit speed, and also he's got a higher launch angle on average. But it's going to be the distribution that's very important, not just the averages that people often will talk about. Now, what we can do is the same thing that we did with the pitchers. The pitchers, we were comparing their pitch parameters in 3 dimensions. We only have 2 dimensions here, so we can use the earth mover's distance in 2 dimensions to figure out how much work's required to transform one player's distribution into the other player's distribution. And the earth mover's distance, the EMD, can be run in any number of dimensions. So as we have more variables, we can just plug them in. At this point, we just have these 2. Okay, and the ground distance, which tells us how to measure the distance between individual elements of the distribution, it's the same idea as with the pitchers, in that the variables have different variances and they have a correlation. So we use the Whitening Transform that's shown here so that we can compare the points on a level playing field as far as not double counting correlation and accounting for the variances. Okay, so we do that, and again, we compute the distances between a pair of batters against right-handed pitching and against left-handed pitching, and then we weight them similar to what we did with the pitchers. This is for 2017, and it turns out the most similar batters overall and the most similar right-handed batters based on these distributions are Andrew McCutcheon and Nolan Arenado. For left-handed batters, it is Mitch Moreland and Shin-Soo Choo. And for switch hitters, it's Indians. Jose Ramirez and Francisco Lindor are the most similar. And we can go through and generate, just like we did for the pitchers, we can generate the unique batters. So these are the 10 most unique right-handed batters in 2017. And probably not a huge shock that we've got Aaron Judge at the top and Giancarlo Stanton not too far behind. And we can generate the same kind of visualization that we had before. For this guy, we've got exit speed increasing going to the right, and we've got the vertical launch angle increasing as we go up. So we see Judge over here at the far right with the high exit speed, and then down a little bit, and to the left, we've got Stanton with a bit lower exit speed and a lower launch angle. We've got Paul DeJong up at the top with a high launch angle, Wilson Contreras down at the bottom with lower launch angles, and then we've got a collection of 4 guys over here on the left side that have the lower exit velocities. So these are your 10 most unique right-handed batters for 2017. For the left-handed batters, these are the 10 most unique. And if we put those on our plot, we've got 3 guys on the right with the highest average exit speeds among guys in the picture here, Schwarber, Duda, and Harper. Harper's got the smallest average launch angle of the 3. We've got Didi Gregorius up at the top with a high launch angle, Cargo down at the bottom with a lower launch angle, and then some guys on the left side over here with lower exit speeds. And these are the switch hitters, most unique switch hitters. And same idea, Morales shows up on the right with the higher exit speed, Santana higher launch angle, Cabrera smaller launch angle, Melky Cabrera. Got Billy Hamilton there and Eric Ibar on the left with lower exit speeds. Okay, so one of the other things we can do with this is we can measure how much batters are changing over time, over really any time interval, but we're doing it here between 2016 and 2017. These are the 10 right-handed batters that changed the most according to our metric. And 6 of these 10 guys were over 30 and lost significant exit speed. So that's Holiday and Lucroy and Longoria and Trumbo and Bautista and Hanley Ramirez. Hanley was also dealing with injuries in 2017. So that's a lot of the bigger changers. Stanton is an interesting case in the sense that Stanton lost a couple miles an hour of average exit velocity. He lost about 3 degrees of average launch angle. So if you're just looking at exit speed and launch angle as 2 numbers, you might think Stanton had a much worse year in 2017. But again, it's not these average exit speeds and average launch angles that matter. What we're trying to emphasize is the distributions that are important. So if you look at Stanton, what happened is he lost about 7 miles an hour on his ground balls, but he gained almost 3 miles an hour on his balls in the air, which is a trade-off that you want, and that's why he had a much better season here in 2017. And somewhat interesting, Marcelo Zuna, his teammate down in Miami, had a very similar change in his batted ball distribution. He had about the same exit speed from 2016 to 2017, but he increased it on balls in the air. It lowered on balls on the ground. Overall, he lowered his launch angle, and you can see that he had a much better season overall in 2017. Some other cases, Hernan Perez lost about 3 miles an hour in average exit speed, even though he's fairly young. When you look to see what happened there, it turns out he made a lot more contact on out-of-zone pitches, which hurt his exit speed. Mike Trout made the list because he had a large, more than 4-degree average increase in his launch angle from 16 to 17. These are the left-handed batters with the most change across the seasons. And 3 of the first 4 here are poster boys for increasing launch angle. Alonzo, Morrison, and Jeanette all had significant gains in launch angle, and they also set new highs in home runs by a significant margin. And Kipnis shows up. He was injured in 2017. We have Parra and Carpenter, who made also big changes in the launch angle. Parra got better. Carpenter rose up to have the highest average launch angle in the National League. He actually got a little bit worse. So it is possible to increase your launch angle too much, perhaps. These are the switch hitters with the most change. And again, we've got a number of guys over 30 who lost significant exit velocity. That includes Eric Ibar and Beltran, Morales, Sweeters, and Walker. We had a couple guys who had big increases in launch angle, Eduardo Escobar and Francisco Lindor. That also led to them setting new career highs in home runs by a big margin. And Jed Lowry is an interesting case here. It turns out he was 33 in 2017, and he had a large gain, about 3 miles an hour in average exit speed. He increased his launch angle on average by several degrees. And if you look at what happened with Jed Lowry, he has the biggest improvement across the 2 seasons in the difference in swinging at in-zone pitches compared to swinging at out-of-zone pitches. So it appears there's 2 ways you can get better as far as batted ball distributions. One might be to spend more time in the weight room. The other way is to just swing at better pitches. Okay, these are the batters with the least change according to the metric from 16 to 17 for right, left, and switch. And we've got Nolan Arenado, Jay Bruce, and Freddie Galvis. And we see that their performance across the 2 seasons was pretty consistent. Okay, so let's look at how we can use this for forecasting batters. This is WOBA on contact between 2016 and 2017 for right-handed batters. And we've drawn in the regression line. Some of the notables, that's J.D. Martinez way up there. This is Stanton. This is Ryan Zimmerman, who did much better in 2017 than he did in 2016. But again, the idea is that there's a lot of scatter, and so if we're just going from a point in 2016 up to the regression line, we can make significant errors in our forecasts. So what we've got here is an example of the Elvis Andrus group for 2016 using the batted ball distributions. And one of the things that you can see is that these are him and the 7 closest. And again, we've got a slope pretty close to 1, which means we expect that somebody with this kind of batted ball distribution to hold up pretty well from 1 year to the next. If you look at Pacoda in 2017 projected Andrus for a significant decline. If you look at the annual that just came out not too long ago, they were shocked, it sounded like, that Andrus blew by his 90th percentile projection for 2017. Okay, but if you look at the batted ball distribution, you look at this, you're not going to be surprised that what he did in 2016 held up pretty well in 2017. So to look more specifically, this is 4 guys from the Andrus group for 2016 and 2017. So the first point here, that's Elvis, and then this is Starlin Castro, and then we've got Jose Abreu and Jose Altuve. And the full regression for each of these guys predicted for 2017 would just be to drop them down to the full regression line there. If we use the group regression that we get from the similarity measure, giving us a better population to project onto, then we get the colored points here for each of the players. And the point is that each of the black points is closer to the colored point than the black point is to the regression line. So you can see it geometrically, or if you like looking at numbers, we've got the numbers on the right. The errors that we would get with a full regression for the 4 players are shown here, and then the errors that we get with the group regression we can see are much smaller given over on the bottom right. Okay, so in summary, we've got a similarity measure based on distributions over physical measurements, and it's implemented using a whitened earth movers distance metric. If you'd like more technical details, they're at an article at Baseball Prospectus. That even links to another article with even more technical details. We're writing up another version with yet more results and details. It should be ready in a few weeks. If you want that, you can get on our mailing list. We'll be happy to send that out. And again, number of applications. There was one just brought up at the last panel for having maybe similarity at some minor league or college level and trying to use that to project how that guy might be best coached or how he might progress moving forward. So we can compare players across time and level. We can optimize performance and health projections. We can use this for matchup modeling. As we said, we can use this for performance modeling. And we can, if nothing else, generate visualizations and leaderboards that can be used to entertain baseball fans. So that's all I've got. If there's time, I can answer questions.